Now that we are able to identify acids and bases, we want to talk about the strength. So we can have either strong acids and bases or weak acids and bases. What is going to determine the strength of acids and bases is how much the acid, for example, or the base, dissociates or breaks apart when placed in water. We can think of it with respect to acids in how many protons are actually transferred. So, for example, if I have 10 molecules of HA, and when I then place HA in water, all of the HA breaks apart and I end up with 10 H3O plus and 10 A minus ions. That means everything is transferred. That is considered a strong acid. If instead I start off with those same 10 HAs, but it's a weak acid, I'm going to end up, for example, with 8 HAs left over. They haven't broken apart. And then I'm only going to make 2 of the hydronium ions, H3O plus, and 2 of the A minuses. So strong acid, everything breaks apart. All of the protons are transferred. Weak acids, only some of the protons will transfer. And then it's the same idea for bases. If it's a strong base, all of the hydroxide ions are broken apart from the metal. If it's a weak base, only some of them are. So we have a pretty short list of strong acids and bases, and that's what we have here in these two tables. So this is strong acids, and these are strong bases. So that means if I have one of these acids, every molecule is going to break apart and give away its hydrogen ions. If I have these strong bases, all of them will break apart and give up their hydroxide ions. Anything else that's considered an acid and base and is not on this table are going to be weak acids and bases. So there are a lot more weak acids and bases than strong acids and bases. Let's do a quick check here. Which of the following equations would be a correct representation of a strong acid when placed in water? So I didn't use the term on the previous slide, so here's a great time to do it. These are equilibrium reactions, which we talked about in the previous chapter. Equilibrium is when the forward reaction and reverse reaction rates are equivalent. They're happening at the same speed. If a strong acid means everything is broken apart, it's going to be product favored. Right? It wants to break apart into ions. It doesn't want to stay as HA, or the acid. If it's weak, it's going to be reactant favored. It's going to stay more as reactants rather than breaking apart. So if I look at my equilibrium arrows here, as that's the only difference in these reactions, here they're equal, meaning product and reaction is the same. Here the forward arrow is bigger than the reverse arrow, so that's product favored. This last one, the reverse arrow is bigger than the forward arrow, so this is reactant favored. So if I just said strong is product favored because it wants to make all products, then B here is your best representation for a strong acid when placed in water. We can represent acid and base strength using ionization constants. So KEQ, something we talked about back in chapter 9, was when we looked at equilibrium reactions and we put the concentration of the products over the concentration of the reactants. The other thing to keep in mind, we do not include liquids or solids. And then coefficients become exponents, if we have any. So we're going to do the exact same thing here, but now we have, instead of KEQ, we have Ka. So this is the equilibrium constant for an acid. So what we have here is a generic acid reaction. We have HA in water. That HA is going to lose its hydrogen ion and transfer it to the water. So that makes the H3O plus, and we are left over with whatever the A minus ion would be. So if I want to write this equilibrium constant expression, we're going to put products over reactants. We're going to not include liquids, so water will not be part of this equation. So I have H3O plus, no coefficient, times A minus, again no coefficient, over HA. So that is my Ka, or my acid ionization constant. Just like with equilibrium constants, if Ka is greater than 1, it's product favored, which we just on the previous slide said is a strong acid. If Ka is less than 1, it is reactant favored, and that is a weak acid. So if we have a table of Ka values, we can then predict if it is going to be a strong acid or a weak acid. So here is a very abbreviated table of Ka values, and the question asks which of the following acids is the strongest and which is the weakest. So we just said Ka greater than 1 is strong, Ka less than 1 is weak. So if we look at the table, we have 10 to the negative third at the top, 10 to the negative 13th at the bottom. Now both of these are less than 1, so they fall on the classification of a weak acid. However, we're looking for strongest and weakest. So I'm not looking for strong versus weak. I'm just trying to rank them strongest and weakest. So the largest Ka, 10 to the negative third, is a bigger number than 10 to the negative 13th. So this is a bigger Ka up at the top. So that means it is a stronger acid. And then down here at the bottom, we have the smaller Ka, so that's the weaker acid. We can verify this with this percent ionization column. So this is what percent of the molecules are broken apart into hydrogen ions. All of these percentages are low, right? 8.3 is a low percent. That would be a weak acid, but that's a lot higher percentage than 0.000065%. Okay, so big difference. Even though these all classify as weak, we do have stronger and weaker acids as well. So the bigger the Ka, the stronger the acid. We can have an equivalent ionization constant for a base. So now instead of Ka, we're looking at Kb. And we're going to do the same thing. We're going to put products over reactants. We're going to ignore liquid. So we've got BH plus times OH minus. So I know this is a base because I'm producing hydroxide, over B. So that base is placed in water. It is accepting a hydrogen ion and producing hydroxide. So it fits both the Arrhenius acid definition because I'm producing hydroxide, as well as the Bronsted-Lowry definition because it's accepting the hydrogen ion or the proton. So here's your Kb equation. Just like with Ka, if Kb is greater than 1, it's strong. If KB is less than 1, it's weak. And we can rank strongest to weakest, bigger KB, stronger, smaller KB, weaker. So here's some questions that kind of make your brain think a little bit. We're talking about two different substances, and we're trying to decide which one, in this case specifically, is looking for the stronger acid. So we have two acids, we have Y and Z. Both of them are monoprotic, meaning they both are going to donate one hydrogen ion. And again, we're trying to find the stronger acid in each pair. So the first one, it says at equal concentrations. That means I have the same amount of Y as I do Z. Y is going to dissociate to a greater extent than Z. So remember, dissociate means it breaks apart. If Y breaks apart more than Z, that's essentially what this sentence is telling me. How do I connect that to strong versus weak? So remember, strong acids break apart all the way. Weak acids don't break apart very much. So if Y breaks apart more, it is going to be stronger than Z. So Y is stronger than Z. Or in this case, it wants to know the stronger acid, so the answer is Y. If we look at the second problem, it says the Ka for Z is larger than the Ka for Y. So Ka for Z is bigger than the Ka for Y. We said the bigger the Ka, the stronger the acid. So that means Z is stronger. Third problem, we have the equilibrium position for the dissociation or the breaking apart of Y lies further to the right than that for Z. So if it lies further to the right, right is products. If Y prefers to make products, more products than Z does, that means Y breaks apart more than Z does. So Y is stronger than Z. Remember, we're always connecting back to strong versus weak, which is all about how much does it break apart when placed in water. So all of these are getting to the same point, but starting from a different spot. So you're trying to connect all the way back to which is breaking up more. Last problem says the proton transfer, and remember proton is H+, when we're talking about acids and bases. The proton transfer occurs to a lesser extent for Z than for Y. So remember, when acids are breaking apart, what they're really doing is transferring their hydrogen ion or transferring their proton. So the stronger acid is going to transfer more protons. So if Z transfers less than Y, that means Y transfers more, so Y is again stronger. Now these types of questions are questions you're going to want to be comfortable with because these will show up on the LO quiz. In this video, we're going to talk about using pKa to think about acid strength. So we've already talked about Ka, and we said that the bigger the Ka, the stronger the acid. But if you remember, Ka's were numbers like 1 times 10 to the negative 26th. These numbers are not really easy to think about and write. So instead, we're going to use what we call pKa. When we talk about pH in a little while, pH is equal to the negative log of the H plus or the H3O plus concentration. Again, we'll get to that. pKa is going to be the negative log of the Ka. So P something usually means negative log of whatever that something is. So if we take the negative log of numbers like this, 1 times 10 to the negative 26, we're going to get whole numbers, things that are a little bit easier to work with. So for example, if I did the negative log of that 1 times 10 to the negative 26, we will get an answer of 26, right? 26 is a lot easier to think about than 1 times 10 to the negative 26. Now, when you do this negative log calculation, what you're going to do is you're going to invert this relationship. So up here we said the larger Ka is a stronger acid. If we're talking about pKa, a smaller pKa is a stronger acid. Okay, so the numbers are easier to think about, but you have to remember now we have the reverse relationship. So we're going to calculate the pKa for HF if we know the Ka is 6.8 times 10 to the negative fourth. So remember, pKa is just the negative log, and this is the base 10 log of that Ka, so 6.8 times 10 to the negative fourth. If we plug that into our calculator, we get 3.17. So how does the pKa change as an acid gets stronger? So remember, Ka, so the bigger the Ka, stronger the acid. Smaller pKa, stronger acid. So as pKa increases, acid strength decreases, and vice versa. If pKa decreases, acid strength increases. So if that's the case, which of the following acids is going to be the strongest? So we've got negative 2.5 is smaller than 4.6 is smaller than 10.3. So the negative 2.5 is the smallest, so it's the strongest. 10.3 is the biggest, so it's the weakest. Now notice this again was a lot easier to do than thinking about those big or really small 1 times 10 to the negative 25 type numbers.